Welcome to Zeta Math. Over this and the next video, we'll discuss this sum, how Euler discovered its surprising value, pi squared over 6, and how Euler went on to prove the sum has this value. Let's jump now to the 1600s, as mathematicians are beginning to understand the notion of infinite series. Recall that to say that a series converges means that the series has a precise numerical value. So, for example, this first series here, this 1 over 1 times 2, plus 1 over 2 times 3, plus 1 over 3 times 4, and so on. If you add all of those numbers together, even though it's infinitely many numbers, the sum as it happens is exactly the number 1. And I'll show you why that's true in a minute. If you take the series 1 minus a half plus 1/3 minus a fourth plus and so on back and forth, this is called the alternating harmonic series. And in fact, this converges. Its exact value happens to be the natural log of 2. On the other hand, if you took the series, which is the same series we just did, but with all plus signs, so 1 plus a half plus a third plus and so on and so forth, this series, which is called the harmonic series, it diverges, because if you add up all of these numbers, the total value that you get is infinite. Let's go back to this series 1 over 1 times 2, plus 1 over 2 times 3, plus 1 over 3 times 4, plus... And so the kth term of this series is 1 over k times k plus 1. I want to make the following clever algebraic note, which is that 1 over k times k plus 1 is the same thing as 1 over k minus 1 over k plus 1. And I'll leave it in your capable hands to check that. And so what that means is that I can replace the first term, 1 over 1 times 2, with 1 minus a half. And the second term, 1 over 2 times 3, with a half minus a third. And 1 over 3 times 4 with a third minus a fourth, and so on forever. But if I now go and redo my parentheses, then it's pretty easy to see that I now have a minus a half plus a half that's 0, a minus a third plus a third that's 0, a minus a fourth plus a fourth that's 0, and so on forever. And so, in fact, everything after that initial 1, that 1 at the very, very start, those things all cancel. And so the value of this series, in fact, is exactly 1. So now I want to look a little bit at Euler's series. That is this 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 and so on. What I want to do is I want to line up the terms of Euler's series with the series that we just computed. Namely, I'll take this 1/4, and I'll notice that 1/4, that's smaller than a half. Likewise, a 9th is smaller than a 6th, and a 16th is smaller than a 12th, and so on down the line. And so what I'm saying here is that if I add up all the numbers in the top row, I get 1, but each number in the second row is smaller than the corresponding number in the top row, and so when I add all of these up, I must get some number that's less than 1. But then the only difference between this and Euler's sum is that Euler's sum starts with a 1. So I can add 1 to the front of this equation, and I'll get that Euler's sum 1 plus a fourth plus a ninth plus and so on and so forth. And that's less than 2. Determining the value of this sum came to be known as the Basel problem. The name is taken from the city of Basel, Switzerland, where the Bernoullis popularized this problem and where Euler ultimately solved it. Roughly speaking, the process that Euler went through to solve this problem had 2 parts. The first was he wanted to approximate the value of the series to enough accuracy that he was able to guess what the number was that the sum was equal to, so that he could then try to prove it. In fact, as we'll go over in just a moment, Euler was able to calculate the value of this series to 17 decimal places, despite the fact that he was centuries before a computer. So in this video, I'm going to explain to you how he did that, and what sort of math he invented along the way, just to be able to approximate this series so accurately. Now, after he calculated these 17 decimal places, he realized, aha, this looks just like the decimal expansion of pi squared over 6. So it must be the case that the thing I'm trying to prove is that this sum is pi squared over 6. So then I just have to figure out how to go about bending and stretching and breaking the limits of math to make that happen. In the next video, I'll discuss Euler's proof that this sum is exactly pi squared over 6. But for now, let's focus on approximating this sum. To get started, I want to visualize this sum graphically as the area of this cascading arrangement of rectangles. Drawing in the graph of y equals 1 over x squared, we can pull out this area and evaluate it as this integral from 1 to infinity of 1 over x squared dx, and that integral we can readily calculate to be 1. If I draw in these diagonal lines, I can also capture the area of this bunch of triangles. I'm going to leave it to you to show that the area of this bunch of triangles is exactly a half. But as a hint, I'm going to show you this picture where I slide all the triangles over to live in the same column. If you're unsure how to proceed, I encourage you to talk about this in the comments. This means that the sum as n goes from 1 to infinity of 1 over n squared, it's 1 plus a half plus the area of these sort of crescent-shaped pieces. If I zoom into this unit length interval from I to I plus 1, then I can calculate the area of this crescent, which I'm going to call A sub I. And it's going to be the area of the trapezoid minus the integral. And so the area of the trapezoid is going to be f of I plus 1 over 2, and then minus the integral from I to I plus 1 of f of x. Thus, our sum as n goes from 1 to infinity of 1 over n squared is this 1 plus this 1 half, and then plus this a1 plus this a2 plus this a3, and so on. Our plan here is that we're going to estimate each of the AIs individually, and then at the end we're going to combine all of it together. So let's go to a zoomed-in view of just one of these AIs. To avoid letting our notation get too cumbersome, I'll let our interval run simply from 0 to 1. But as you'll see, by the end of this, it won't matter what the interval is. To emphasize that this works for any function, I'm just going to call the function here f of x. I'm going to call the area of the crescent A. And I want to remind you here that A, in this case, is given by f of 0 plus f of 1 over 2 minus the integral from 0 to 1 of f of x dx. What we're going to do is rewrite this integral from 0 to 1 of f of x using a clever integration by parts. Okay, so here we go. We're assuming f is just some differentiable function, and I want to rewrite this integral from 0 to 1 of f of x using integration by parts. Now, this might seem a bit strange, as you might remember that usually you apply integration by parts to a product of things, and even more strange because we don't know anything about f of x, but bear with me for a minute and I'll show you how this is going to work out. So I want to remind you what integration by parts says in this case. Namely, if you take the integral from 0 to 1 of some function u times the derivative of some function v, then what you get is the product function uv evaluated at 1, then minus that same product uv evaluated at 0, minus the integral from 0 to 1 of v du. So the whole application of integration by parts comes down to choosing what we want to be our u and what we want to be our v. Usually what we do when we're integrating by parts is to start by choosing a u and a dv. So that is, we choose two functions that multiply together to be the function that we're integrating. In this case, the function we're integrating is f of x. So the only real way I can write that as a product is as f of x times 1. In this case, I'm going to choose u to be f of x and dv to be 1. Once we've chosen u to be f of x, then du is just the derivative of that, so it's f prime of x. And we've chosen dv to be 1, and so our natural inclination is to take v to be the antiderivative of 1, namely x. But I want to remind you that in fact 1 has lots of antiderivatives. Namely, not only x, but x plus any constant. In this case, for reasons that we'll see very shortly, if we choose the constant minus a half, that is, if we choose v to be x minus a half, then things work out well. Alright, so let's apply the formula. So, our formula gives us that we have uv, which is f of x times x minus a half, evaluated from 0 to 1. I'm just going to leave the integral here as the integral from 0 to 1 of v du, because the reason why this x minus 1/2 is going to be so nice has everything to do with what's happening here with this term at the front. So I want to focus on that for now. In particular, when we plug in 1, we get f of 1 times 1 minus a half, minus, and then when we plug in 0, we get f of 0 times 0 minus a half. And of course, we still have the minus the integral from 0 to 1 of v du piece. Now, f of 1 times 1 minus a half, that's just f of 1 over 2. Similarly, f of 0 times minus a half is minus f of 0 over 2. But we also have this minus, and so together, that gives us two minuses, which means we get a plus, which means this second term here is plus f of 0 over 2. And so these two pieces together give us f of 1 plus f of 0 divided by 2. And then we have minus the integral from 0 to 1 of, and I'll go ahead and write it out this time, x minus a half times f prime of x dx. I'll bring back this sheet of paper where we were writing down our original formula for a, and remind you that what we just did was to rewrite the part underlined in red, namely we rewrote the integral from 0 to 1 of f of x dx. So I'm going to now plug in what was our result from before. So that's going to give us f of 0 plus f of 1 over 2, minus, and then f of 1 plus f of 0 over 2, minus the integral from 0 to 1 of x minus a half times f prime of x dx. And here is where the magic happens. Namely, our opening f of 0 plus f of 1 over 2 is exactly canceled by our new f of 1 plus f of 0 over 2. And so at the end of the day, we're left with a very simple formula for a, namely that a is just the integral from 0 to 1 of x minus a half times f prime of x dx. Why did this work out so nicely? Why c equals minus a half? To understand that, we have to go back to what our formula for a looked like immediately after we integrated by parts, before we did anything else. So I'm going to write that here as a equals, and then we had this part from the trapezoid, this f of 0 plus f of 1 over 2, then minus this uv term, evaluated from x equals 0 to x equals 1. That's the part out of the integration by parts that eventually ends up canceling with this first term, and we want to understand why. And then we have plus this integral from 0 to 1 of x minus a half times f prime of x dx. To understand why we get so lucky, I want to focus on what happens when f of x is linear. In this case, it's clear from the geometry that a equals 0, so we can just cross it out here. On the other hand, let's look at what happens to the integral when f is linear. In this case, f prime of x is just a constant, so let's call it little c. Thus, we can pull this out of the integral, so we're left with just little c times the integral from 0 to 1 of x minus a half dx. But this integral is 0. Thus, returning to our formula, we can cross out the integral term too. But now, it follows immediately that the f of 0 plus f of 1 over 2 term and the uv evaluated from x equals 0 to x equals 1 term must exactly cancel each other out, as we saw above. So just to emphasize, why x minus a half? Because that's the only antiderivative of 1 we could have chosen whose integral from 0 to 1 is 0. So what I'd like to do here is integrate by parts again. So here I'm going to set u to be f prime of x. So du is f double prime of x. And dv is going to be x minus a half. So then v is going to be x squared over 2 minus x over 2. And then plus a constant. And this time I'm going to just leave this as plus a constant, and I'm going to let us figure out what we want that constant to be. So take a brief moment to relax while I churn through the integration by parts formula here. Having done that now, we see that we get that a is c times f prime of 1 minus f prime of 0 minus the integral from 0 to 1 of f double prime of x times x squared over 2 minus x over 2 plus c. I want to emphasize here that this equality is true for all values of c. No matter what constant I choose for c, this is a true statement. So which c should I pick? At first, maybe you're thinking, oh, we can pick c equal to 0, because if we pick c equal to 0, then the first term goes away. But actually, the first term is easier to contend with than the second, because the first term is just evaluating some information about our function at 1 and 0, namely the derivative. But this integral is a pretty complicated integral because it's some complicated combination of polynomials. So what I want to look back to is I want to look back to what happened in the previous step, where we noted that if f was linear, f prime was constant, and then this minus a half factor turned out to make the whole integral vanish in the case that f was linear. If f is quadratic, then f double prime is a constant. I'm going to call that constant little d, just so we don't confuse it with our big C over here. So I can pull the little d out of the integral, which will give me the integral from 0 to 1 of x squared over 2 minus x over 2 plus c. Can you see where this is going? Just as before, I'm going to choose my constant c so that I can make this integral equal to 0. In this case, the c that makes this happen is c equals a 12th. Thus, if we choose the constant c to be a 12th, then we'll make sure that this formula for a is this piece at the front with the derivatives, but then this integral part just completely disappears. I want to go ahead and give a name to this process. For a polynomial little p of x, we define script a p of x to be the unique antiderivative big P of x, such that the integral from 0 to 1 of big P of x dx is 0. I encourage you to work out the details for yourself to convince yourself that for every polynomial little p of x, this script a p of x is a well-defined polynomial. Here are our three formulas for a so far. From the first to the second, we've pulled the linear part of f out of the integral. And when we did that, it canceled with this front term. From the second to the third, we pulled the quadratic part of f of x out of the integral, and that gave us this term. We want to understand how we can continue this process. So that is, how we can pull the cubic and quartic and quintic parts of f of x out of the integral. Each part of f that I pull out of the integral is going to give me a new term here up front. And I'm going to call all of the terms here up front collectively the boundary terms. And the reason why I'm calling it the boundary term is because it only depends on what happens on the boundary of the interval from 0 to 1 that we're talking about here. Namely, the points 0 and 1 themselves. Nothing about what happens between 0 and 1. We're going to call this the 0th formula for a, this the first formula for A, this the second formula for A, and so we're looking to figure out how we can find the third, the fourth, and so on formula for A. So I want to start keeping track of the things I'm using as the v in the integration by parts. I'm going to call the little v in the kth integration by parts big V sub k. So in the formulas you can see this is my v0, this is my v1, and this is my v2. So what's our general kth formula going to look like? My kth formula is going to look like A is equal to, and then I'm going to have a sum of boundary terms, one for each time we've done this. So bt1 plus bt2 plus up to btk minus 1 plus, and then some plus or minus 1 times, and then the integral from 0 to 1 of our v sub k times the kth derivative of f dx. Note our second formula here for A already has this form, with bt1 equal to f prime of 1 minus f prime of 0, all divided by 12. Okay, so what I want to do now is I want to give sort of an inductive definition of what the kth step here is going to look like. So the way I'm going to do that is say, well, I've already shown you what the first two steps look like. And then I'm going to show you, if you've already taken some number of steps, how do you go one step further? Here we have our formula for A, which is the sum of some boundary terms, plus minus 1 to the k plus first power times this integral involving the kth derivative of f. And what we'd like to do is figure out how to change this into a formula, again with some boundary terms, but instead with an integral in terms of the k plus first derivative of f. And so not surprisingly, what we're going to do here is we're going to integrate by parts. So I'm going to pull out this integral, and then we're going to do this integral by parts. As we've done each time before, we're going to take u to be the f part, in this case the kth derivative of f, and we're going to take dv to be this v part, the v sub k. So then du is just the k plus first derivative of f, and for v, I'm going to take this thing that we called a of vk of x. That is, we're going to take the antiderivative of vk of x, whose integral from 0 to 1 is equal to 0. And I'm going to call that thing v sub k plus 1. So what does that give us? It's going to give us the kth derivative of f times v sub k plus 1, evaluated at 1, then minus that evaluated at 0, and then minus the integral from 0 to 1 of v sub k plus 1 times the k plus first derivative of f. And now we're going to plug this formula that we just got out of the integration by parts back into our original formula for A. And so here, after we notice that I can pull this minus into the minus 1 to the k plus 2, so we've returned to the form we wanted, but now our integral involves the k plus first derivative of f instead of the kth derivative of f. And one nice thing about having written it this way is that now we know what the kth boundary term is. Namely, it must be that this piece I'm underlining in blue is the kth boundary term. And so we can record that formula for the future. Using this formula for the boundary terms, we have the following expression for our kth formula. In terms of only the kth derivative of f, which is part of an integral, and the values of the derivatives of f up to the kth derivative of f at 0 and 1. To summarize, our kth formula has the following two key properties. First, the boundary terms here depend only on f and its derivatives evaluated at 0 and 1, nowhere in between. Second, the integral term vanishes if f is a polynomial of degree less than or equal to k. Be sure you understand what both of these points are saying and why they're true before we proceed. Now, Euler did all of this calculation by hand, so let's do at least a little bit of this to show you that it is possible. So I've got, again, v0 is 1, v1 is x minus a half, v2 is x squared over 2 minus x over 2 plus a 12th. So what am I going to do to find v3? Well, I have to calculate, remember, this a of v2. So I'm going to write down this antiderivative. So that's going to be x cubed over 6 minus x squared over 4 plus x over 12. And now plus a constant, and I need to solve for this constant because remember I need to make it so that the integral from 0 to 1 of this thing that I have left is 0. So let's go ahead and calculate that integral. So the integral from 0 to 1 of this polynomial I just wrote down is x to the 4th over 24 minus x cubed over 12 plus x squared over 24 plus whatever our constant is times x. But I'm evaluating this from 0 to 1, so I get to plug in 1 and then subtract off what I get when I plug in 0. Note, conveniently, when I plug in 0, everything just disappears, so I just get 1/24 minus a 12th plus a 24th plus c, which is to say that I get just 0 plus c. And so that means the constant I'm looking for here is actually 0, and so I get my formula for my v3. It's x cubed over 6 minus x squared over 4 plus x over 12. If I want to think of this graphically, we're going to take a look at the graph of the quote-unquote obvious antiderivative of x squared over 2 minus x over 2 plus a 12th, namely x cubed over 6 minus x squared over 4 plus x over 12. As before, I'll go ahead and shade the part above the axis and the part below the axis and calculate the integral. And before we moved it up and down, but in a minor miracle here, the integral is already 0, so I don't have to touch anything. So in other words, I can choose as my constant of integration c here, c equals 0. That's what we just saw algebraically, but in the graph. I'll let you watch me continue to do this 1k at a time. Each time, I'm taking the antiderivative of the previous v sub k, and then I'm integrating that antiderivative from 0 to 1. So if you look at this page after page, what you'll notice is basically every time I have to integrate twice in order to solve this. But after I integrate the antiderivative from 0 to 1, then I solve for the constant to just make that integral 0. And so my hope is that you can see that even if this looks a bit messy, you can see that this is definitely something very concrete that you can do. Speaking of messy, as this keeps going by, this is getting really messy. And there's a good reason for that. Namely, if you look at this first term here, this x to the k term, it always has a denominator of k factorial. So the denominators involved in our v sub k's are growing very quickly. And so that's making this polynomial look a little bit more complicated than it has to be because it has this ugly denominator floating around from the beginning. Because of this, we tend to normalize these polynomials by multiplying through by k factorial, which also makes them way easier to work with. So to be super precise by what I mean, I'm going to define a new list of polynomials. I'm going to call these b sub k. And my b sub k is just going to be literally equal to k factorial times the v sub k. These things are known as the Bernoulli polynomials. And we'll discuss later exactly how Bernoulli happened upon them, but as you can see, these things are much more palatable than the polynomials we were calculating before. I should make a quick note about how we go about calculating the Bernoulli polynomials without thinking about the v sub k's. So in other words, I have to explain how to get from b sub k to b sub k plus 1. So to do that, I'm going to write down this system of equations, basically. My b sub k plus 1, it's k plus 1 factorial times v sub k plus 1. That's just the definition. My b sub k is k factorial times v sub k. It's also just the definition. And my v sub k plus 1, that's this a operator of v sub k. It's also just our definition. I'm going to substitute that last equation into the first one to get that b sub k plus 1, it's k plus 1 factorial times this a operator of v sub k. Now remember, my goal is to not mention the v sub k's, So I can rewrite v sub k as being b sub k over k factorial. That's by the second equation over here. And so then I get that b sub k plus 1 is now k plus 1 factorial times the a operator of b sub k over k factorial. But the over k factorial is just a constant, so I can pull that out of the whole a operator business. And so what I'm just left with is that b sub k plus 1, it is k plus 1 times the a operator of b sub k. In other words, the process for generating the b sub k's is almost identical to the one we used to generate the v sub k's, but with this small extra step where I have to multiply by k plus 1 at the very end. So from our calculations above, the sixth Bernoulli polynomial is this. So my script a of the sixth Bernoulli polynomial is going to be this, and I still need to solve for this plus c. To do that, I'm going to integrate this script a of b6 from 0 to 1. I set that equal to 0, and then I solve it. And so this c I'm looking for turns out to actually be 0. And so, by what we said before, b7 is 7 times this script a of b6 we just calculated. And so we get this for b7. You can watch me do the same thing for calculating b8, albeit at a much faster pace. And you can imagine continuing on through this process and calculating progressively more of these polynomials. Let's bring back our formula for the area A from earlier. And now this still has the v sub k plus 1s in it. I don't want to think about those anymore, so I'm going to rewrite all of them in terms of the b sub k's, which is going to leave us with this. Now, I want to look at something and note that b sub k, it's a polynomial, but if I ignore the integral part at the end, I don't actually care about the polynomial, I only care about the value of the polynomial at 0 and 1. In other words, to say that again, the boundary terms don't care about the polynomial, the boundary terms only care about the value of the polynomial at 0 and 1. So pulling up this table of the Bernoulli polynomials that we've generated, I'm going to go ahead and fill in the value of them at 0 and at 1. Now, almost as soon as I do that, there's a couple patterns that really leap out at you. So the first pattern you probably notice is that the value at 0 and the value at 1 seems to always be the same. To prove this, we're going to evaluate the integral from 0 to 1 of b sub k minus 1 of x in two different ways. Before we do this, I just want to recall on screen here that our definition of the Bernoulli polynomials is that b sub k plus 1 is equal to k plus 1 times the script a of b sub k. Thus, we can go ahead and rewrite the b sub k minus 1 in the integral as k minus 1 times script a of b sub k minus 2. Upon doing that, k minus 1 is a constant, so we can pull it out of the integral, but now we're left with the integral from 0 to 1 of the script a of b sub k minus 2 of x dx. But remember, by our definition of script a, this is exactly 0. And so this integral we started with, it's 0. On the other hand, I could notice that b sub k of x, that's k times script a of b sub k minus 1 of x. And in particular, what that means is that b sub k of x divided by k, that is an antiderivative of b sub k minus 1. And so we can evaluate this integral with the fundamental theorem of calculus. And what do we get? We get that the integral from 0 to 1 of b sub k minus 1 is b sub k of 1 over k minus b sub k of 0 over k. But on the other hand, we already know this integral is 0, and the only way that can happen is if b sub k of 1 and b sub k of 0 are equal, which is what we hope to show. So there's no reason to have two columns in this table, so I'm just going to merge the columns together. And in fact, the kth entry in this row, that is the kth Bernoulli polynomial evaluated at 0 or 1, That's usually called the kth Bernoulli number, and it's usually denoted by a lowercase b sub k, so we're going to do that as well. With this definition, if we look back at our kth formula for A, now we can rewrite big B sub k of 1 and big B sub k of 0 as just little b sub k everywhere they appear. And once we do that, we can factor the little b sub k's out of each term, and then we're left with this. But almost certainly, that's not the only pattern that you notice looking at this table. If I remove the polynomials and just list the first 25 Bernoulli numbers, you're probably going to be pretty convinced that b sub k is 0 whenever k is odd, as long as k isn't 1. And you might already have noticed there's all kinds of weirdness with the first Bernoulli number anyway. The proof of this result is actually pretty neat. I'm going to leave this to you to discover. Feel free to discuss it in the comments. But I'm just going to take for granted that you've done this exercise, and then I'm going to remove all of the odd terms from our formula for A. I want to point out that that actually makes things a lot nicer, because it gets rid of all of these alternating signs that I've been generously keeping track of for you throughout this video, but now all of them disappear, and so we're just left with this cleaner looking formula. Now, if you're following the thread here, you'll remember that my stated goal was to approximate this sum, which makes it a little weird, perhaps, that I've done all of this work and there's still an equal sign here. This statement here is exactly correct. And I want to note this first term here, it's easy to calculate. This next term here, it's easy to calculate, and so on. In particular, the function f that I'm actually interested in applying this to is 1 over x squared. So I'm happy to take any number of derivatives of 1 over x squared that you want. 100 derivatives, no problem. The part of this that's not easy to evaluate is this ugly-looking integral piece here at the end. And so, the way that I'm going to make this an approximation is that I'm just going to agree that I'm never going to evaluate this integral. And so I'm going to throw this away and replace this nice equals with a squiggly equals. Now, my hope is that because at this point I've pulled out all the stuff of degree 2, 3, 4, 5, up to whatever 2k I happen to have chosen from the integral, that hopefully whatever is left in the integral is small enough that this approximation is good. And so then the integral will be small and we can just forget about it. So far, we've been focused exclusively on the interval from 0 to 1. And our conclusion here is that this a for the interval from 0 to 1, that's f of 0 plus f of 1 over 2 minus the integral from 0 to 1 of f of x dx, that's well approximated by this formula, which involves the Bernoulli numbers and the derivatives of f at 0 and 1. Now, if you rewind back to way earlier when we talked about this situation, we actually had these a sub i's representing the area of the same region, but over the interval from I to I plus 1. So the key here is that I want to not have to find a new formula. I want to be able to basically apply the formula we already have to work on the intervals from I to I plus 1. And so here the key to us doing that is to remember I didn't assume anything specific about the function f in doing this calculation, other than I guess that I could take this many derivatives of it. So what I'm going to do here amounts to a change of variables, just so that I can move this interval over to the interval from 0 to 1. Namely, I'm going to define this function f sub plus I of x, and the value of this function at x is just going to be the function f evaluated at x plus I. If you think back to your rules about transformations of graphs, the graph of f sub plus I of x is just the graph of f of x shifted to the left by I units. In particular, this shifts the graph so that the interval in f from I to I plus 1 is now squarely in the interval from 0 to 0 plus 1. To see this in equations, I'm going to rewrite this formula for AI that we have as f sub plus I of 0, it's just a different way of writing f of I, a weirder way, plus f sub plus I of 1 divided by 2, minus the integral from 0 to 1 of f sub plus I of x dx. Now this is exactly the kind of thing that our formula tells us how to approximate. And so I'm going to apply that approximation here, giving us that AI is approximately the second Bernoulli number times f sub plus I prime of 1 minus f sub plus I prime of 0 over 2 factorial plus, and then we've got this term with the fourth Bernoulli number, and so on. But now it's not so hard to see that f sub plus I prime of 1 is the same thing as f prime of I plus 1. Use the chain rule if you're unsure where this is coming from. And so now I'm just going to clean up all the evidence that I ever mentioned the sub plus I business, and I'm going to replace everything back so that I get that a sub I, it's approximately b2 times f prime of I plus 1 minus f prime of I over 2 factorial plus b4 times f triple prime of I plus 1 minus f triple prime of I over 4 factorial, and so on. Let's return to Euler's context. That is, let's set f of x equal to 1 over x squared. And so remember that what Euler is trying to do here is to approximate the sum as n goes from 1 to infinity of f of n, which, as we showed before, is this 1 plus this a half plus a1 plus a2 plus ... and so on. Now I'm going to break out each AI here into the approximation that we gave just now. You'll see that at first, this looks pretty messy. However, if you squint closely at this, you'll notice that it's not nearly as bad as it looks. So for example, if you look at this b2 times f prime of 2 over 2 factorial here, it's exactly canceled by this b2 times minus f prime of 2 over 2 factorial here. Likewise, this b2 times f prime of 3 over 2 factorial is canceled by this minus b2 times f prime of 3 over 2 factorial, and so on. And this happens in every column. And at the end of the day, all that's left is the terms that specifically involve the derivatives of f at 1. Everything else washes away. And so after all of that has washed away, here's what we're left with. We're now left with the sum as n goes from 1 to infinity of 1 over n squared. It's approximately 1 plus a half minus b2 times f prime of 1 over 2 factorial minus b4 times f triple prime of 1 over 4 factorial, and so on. I'll go ahead and show you a few derivatives of 1 over x squared. So if f of x is 1 over x squared, f prime of x is minus 2 over x cubed, f double prime of x is 6 over x to the fourth. And it's not so hard to convince yourself that indeed the kth derivative of this f is always minus 1 to the kth power times k plus 1 factorial divided by x to the k plus 2. Now remember that we're going to be evaluating this derivative at 1, and it's going to be appearing in our formula here. However, if you evaluate this at 1, then what you find is that the kth derivative of f at 1 is minus 1 to the k times k plus 1 factorial. Now, in general, k plus 1 factorial is going to be a pretty big number, which means that our approximation is not going to settle down quickly. And we would like, of course, especially if we're Euler doing this by hand, to use as few terms as we possibly can here. So the first thing I'm going to do is I'm going to break my sum as n goes from 1 to infinity of 1 over n squared into two pieces. One piece where n goes from 1 to 9, plus one piece where n goes from 10 to infinity. Now the first part here, the sum as n goes from 1 to 9, that is just a sum with 9 terms. So I can write these all out, and all of their decimal values, and then we can add them together. And so here, to 20 decimal places, is the sum as n goes from 1 to 9 of 1 over n squared. So now let's go back and let's look at the sum as n goes from 10 to infinity of 1 over n squared. So we pull up this graph again, where the area of the bars in aggregate is the sum as n goes from 10 to infinity of 1 over n squared. And so again, we break up that area into the part that's under the curve, which will be the integral from 10 to infinity of 1 over x squared, which is a tenth, or if we're doing stuff in decimal now, 0.1. We've also got all of these triangles floating around. And now you can check the total area of all of these triangles. It's now 1/200th, or 0.005. Now the slivers, that is the A10, the A11, the A12, and so on, those are almost invisible in this picture. And remember, we're trying to get a really, really accurate approximation. So even though they're almost invisible in the picture, we still need to take this into account. So we need to approximate A10 plus A11 plus A12 plus and so on. And just like we did earlier, if we replace each of these AIs with our approximation from before, and sum them all together, then just as before, everything telescopes. That is, everything cancels except for the stuff that involves derivatives of f at 10. And so we get that this sum of the AIs starting at A10, it's approximately minus b2 times f prime of 10 over 2 factorial, minus b4 times f triple prime of 10 over 4 factorial, and so on. Remember that before we showed that the kth derivative of f is minus 1 to the k times k plus 1 factorial divided by x to the k plus 2. And so the kth derivative of f at 10 is minus 1 to the k times k plus 1 factorial divided by 10 to the k plus 2. Now if we plug this into the formula above, what we see is that in fact we have 2 factorials in every term, one in the numerator and one in the denominator, and so those all wipe away and cancel. And so we're actually now left with that if I sum the AIs starting at A10, what I get is approximately just b2 times 1 over 10 cubed plus b4 times 1 over 10 to the 5th plus b6 times 1 over 10 to the 7th plus and so on. If you were wondering before why Euler chose to pull out 9 terms rather than, say, 10 terms or some other number of terms, you can see here that actually pulling out 9 terms means that these things are going to look a lot nicer when we write them in decimal. Which, if you're about to do all of this by hand, as Euler was, is very important. And so here it is, Euler's approximation of the AI starting from A10 forward, using k equals 9. So we have here the first term b2 times 1 over 10 cubed, all the way running up to b18 times 1 over 10 to the 19th. If I go ahead and fill in for you the values of those Bernoulli numbers up till then, we get this. And you can see here that the Bernoulli numbers actually get a little less nice than they appear to be at first. And I want to be honest with you, I can in no way imagine calculating this sum by hand to 20 decimal places. But Euler did. And upon doing that, he gets this number. Now remember, we need to combine this number with our running tally from before. And upon doing that, we get this, which is Euler's final approximation of the sum of the reciprocals of the squares as n goes from 1 up to infinity. This approximation is remarkable. It is accurate to 17 decimal places. Imagine that you actually calculated this sum in the naive way. That is, you added the first term, the second term, the third term. Imagine that you were really patient. Like, really, really patient. So you somehow meticulously calculated the sum of the first 10 trillion terms of the series. If you did that, your answer would still only be accurate to 10 decimal places, even with 10 trillion terms. Whereas Euler, by adding together just these 9 numbers, was able to get it accurate to 17 decimal places. And that shows you just how powerful this method is. And it convinced Euler that the sum had to be pi squared over 6, because it agreed with pi squared over 6 to this many decimal places. The method we've described here is now known as Euler-Maclaurin approximation. It was actually independently discovered by both Euler and Maclaurin at around the same time. And what it does here is to explain the relationship between this sum and this integral. This method shows up a lot in math, in particular where either the sum or the integral is easy to compute. In our case, the integral was the one that was easy to compute. But you're interested in the other one. That is to say, in other cases, you might know a lot about the sum and then be interested in information about the integral, so you can use everything we just did but backwards. I should also note that Euler-Maclaurin isn't just an approximation method. Remember that every formula we wrote down until the very end when we kicked off that integral and decided not to evaluate it, all of those formulas were exact. And so it's worth noting that Euler-Maclaurin and the ideas behind it appear as part of a lot of proofs in analytic number theory. Let's talk just a little bit about the error that we introduce when we drop the integral piece at the end. In other words, what I'm really asking is, how big is that integral at the end going to be? Because remember, with the integral, the formula was exact. So what I've shown you here is a graph that tells you how many digits of accuracy you get if you use k terms of this sum above. So for example, Euler used k equals 9 terms, so you can see this point here shows you that Euler got 17 digits of accuracy. In this graph, you can see, as we saw before, that you really quickly reach the 17 digits of accuracy. But then, sort of mysteriously, improvement just seems to stop, and things go flat. But if we broaden our view, we'll see it's actually much worse than that. Because by the time we use k equals 100 terms, rather than having the approximation be astronomically accurate, which is probably what you would expect, instead we see that we're now getting a negative number of digits of accuracy. And you might pause for a second and ask, what does that even mean? But that means the digits before the decimal place aren't even right. One of the really weird properties of Euler-Maclaurin approximation is that this almost always happens. Namely, any infinite sum we want to approximate, we tend to dive in really, really close to the actual value, but then hang there for a little bit, and then diverge. To wrap up this video, I want to discuss how these things came to be known as Bernoulli numbers and Bernoulli polynomials. Because as these names suggest, Euler and Maclaurin were not the first people to discuss these particular polynomials and the numbers associated with them. Indeed, Bernoulli in Switzerland and Seki Takakazu in Japan happened upon these numbers and polynomials independently when they were answering a particular natural question. Namely, they were trying to answer the question, if I sum the kth powers of the first n integers, what do I get? So, for example, you probably know that if you sum 1 plus 2 plus 3 plus up to n, that would be the sum of the first powers of the first n integers. Then you get n times n plus 1 over 2. And likewise, you might know that if you sum the squares of the first n integers, then you get n times n plus 1 times 2n plus 1 over 6. Now, you might even know that if you sum the first n cubes, you get exactly this, which weirdly as it happens is exactly the square of the sum of the first n integers. So what did Bernoulli and Seki want to know? They wanted to know, okay, if I sum the first n kth powers, what do I get? Now, I'm not going to go into much depth here, but if you want to know a lot more about this, I really recommend checking out this Mathologer video, where he goes into this in much more depth. The key observation here is that the Bernoulli polynomials have this unexpected property that if you integrate the kth Bernoulli polynomial from x to x plus 1, then you always get exactly x to the kth power. Now, I'm going to leave verifying that this identity follows from our definition of the Bernoulli polynomials as an exercise for you. But once you do that little exercise, then I can rewrite the sum 1 to the k plus 2 to the k plus 3 to the k plus ... plus n to the k as the integral from 0 to 1 of the kth Bernoulli polynomial, plus the integral from 1 to 2 of the kth Bernoulli polynomial, plus the integral from 2 to 3 of the kth Bernoulli polynomial, and so on, up until I get to the integral from n to n plus 1 of the kth Bernoulli polynomial. But, of course, once you see this giant list of integrals like this, we can zip them all together. And so it turns out that this sum on the left is just given by the single integral from 0 to n plus 1 of the kth Bernoulli polynomial. But even more impressive here is that I know an antiderivative of the kth Bernoulli polynomial, namely the k plus first Bernoulli polynomial divided by k plus 1. And so I can use the fundamental theorem of calculus here to evaluate the integral from 0 to n plus 1 of the kth Bernoulli polynomial. And what I get is the k plus first Bernoulli polynomial evaluated at n plus 1 divided by k plus 1 minus the k plus first Bernoulli polynomial evaluated at 0 divided by k plus 1. Now, of course, you might notice the k plus first Bernoulli polynomial evaluated at 0, that's just exactly what we define the k plus first Bernoulli number to be. Or, if you want to think about it a different way, it's just the constant term of the k plus first Bernoulli polynomial. So really what this is saying is that in order to sum the kth powers of the first n integers, all you have to do is start with the k plus first Bernoulli polynomial, throw away the constant term, because that's the k plus first Bernoulli number, plug in n plus 1, that is one more than the number you wanted to evaluate, and then divide by k plus 1. And voila, that will give you an exact formula for the sum of the kth powers. So just to check this, we'll bring back what's often known as Gauss's formula for the sum of the first n integers, even though Gauss was 2,000 years too late to be the first person to write this formula down. So according to our formula here, we're supposed to start with the second Bernoulli polynomial, which is x squared minus x plus a sixth. But then we're supposed to subtract off the constant term, so that's just x squared minus x. And now we're supposed to plug in n plus 1, which if you do, then we'll get n squared plus 2n plus 1 minus n minus 1, which is n squared plus n. And of course, if you divide n squared plus n by 2, then you get n times n plus 1 over 2, which is exactly our usual formula here. I'll leave it for you to check that this gives you the correct formula for 2 and 3 and however far down this list you want to go. That's all for this episode. Join us next time where we'll pick up the story with Euler again, where Euler now knows that he's trying to prove that this sum is pi squared over 6. And we want to investigate carefully exactly what that proof looks like. And then it turns out, by somewhat remarkable coincidence, that Euler's proof of the value of this sum turns out to be connected to a lot of important ideas. In particular, it is very closely related with the contents of Riemann's 8-page paper in which he outlines and originally states the Riemann hypothesis. And so we'll discuss that, and Riemann's explicit formula, and all of that next time. Thank you for watching. Our theme music was composed by friend of the channel, Keith Welker. So thanks, Keith. Please leave a thumbs up and a comment if you liked the video, and subscribe so that you'll be notified when we post videos like this in the future. But for now, until next time, be well.